Hello and welcome to presentation 4 for ENGI 305. Today we'll be talking about controlled charts in SAS Jump. So first we're going to discuss the different types of control charts using the CLIPS 1, airport, and failure data sets. First we'll talk about the X-bar and R chart for inline production. Then we'll move into discussing the UWMA and EWMA. Then we'll discuss the Pareto chart. And then finally, we'll not only analyze the results of each of these charts, but we'll discuss how they are used to improve production. First, we'll be discussing the X-bar and R charts. These can allow us to monitor whether our process is in control. The X-bar chart shows the mean or average changes of the process over time. The R chart shows how the range of the subgroups changes over time. We can use these in conjunction with one another to make sure our process is in control. For example, if our mean is fluctuating outside of the specification limits, this is a very obvious sign that our process is out of control. On the other hand, we may have a very good mean. However, the R chart could show that the range is very wide. Hence, both of these should be used to quality monitor inline production. You can use the X-bar and R charts when the following statements are true. First, you need to assess need to assess system stability. The data must be in variable form. The data must be collected in subgroups larger than 1 but less than 11, and the time order of subgroups is preserved. We made an X-bar chart and R chart reporting on the delays at an airport in SAS. So we're going to go there now and create them for you. So we know that we are out of control when the data points on the X-bar and R charts appear in such a way that violates any of the Westguard rules. We can select our Westguard rules in SAS by using the action arrow and selecting Westguard rules. When there are red circles around the data points, this indicates that a Westguard rule is violated at that given point. Some Westguard rules are warnings that a process may be out of control or heading towards that direction, while some indicate that the process is clearly out of control. Because you can see that they fall outside of the upper control limit, it's pretty obvious that this process is out of control. Now we're going to talk about the UWMA and WEMA charts. Now the UW and EWMA charts are used in quality control applications too. Both charts can be used to monitor small shifts in the process mean and whether the mean level of the process is in control. UWMA stands for Uniform Weighted Moving Average. The UWMA requires a fixed subset size, the number of successive observations, or span, in the moving average. Span must satisfy the inequality 1 is less than span is less than or equal to n in the sample size. A small span reduces the influence of older observations. A large span slows the response to large shifts. In general, the magnitude of the shift to detect and the span are inversely related. EWMA stands for Exponentially Weighted Moving Average. The EWMA has a weight for the most recent observation. The weight must satisfy the inequality 0 is less than the weight, which is less than or equal to 1. The default weight is equal to 0.2. The best value is a matter of personal preference and experience. A small weight reduces the influence of the most recent sample. A large value increases the influence of the most recent sample. A value of 1 reduces the chart to a Schuhart X-bar chart. Weight between 0.05 and 0.25 is recommended. When designing it, it is necessary to consider the average run length and shift to be detected. Now we're going to use the CLIPS 1 data set to create our UWMA and EWMA charts. These charts display how the UCL and LCL change over time and display when the sample is out of bounds at a given time. In the UWMA, we can see clearly that the process appears to be out of control since, for example, the data point at sample 7 is above the upper control limit. And this is also confirmed by the EWMA. It looks like right on the edge, but the UWMA definitely confirms it. Now we're going to discuss the Pareto chart. A Pareto chart shows the severity of problems using their frequency of occurrence. We will discuss the Pareto plot using the failure data set in SAS Jump. So this Pareto plot will highlight the main causes of failure by indicating the relative frequency that a particular failure occurred on the y-axis using vertical bars, and the corresponding failure specified on the x as shown. With a Pareto plot, the causes are listed in decreasing order of frequency from left to right across the graph on the x-axis. The line shows the cumulative frequency. Notice how the line slope changes as the cumulative percent increases, since the relative relative frequency of the failure causes are decreasing. Thus, this shows that contamination was the most frequent reason for failure, while doping and silicon defect were the least frequent reasons for failure. So now we will discuss what our results mean for improving our inline production. When the range is out of control, this indicates that we should contact process engineering. If the X-bar chart is out of control, we should look to make sure our process was set up correctly, such as, for example, checking that the temperature was set right and checking other settings. And we should also see if we can determine the root cause of failure. We could take a similar approach as the X-bar chart for the EWMA and UWMA charts, since they also measure the mean, and try to determine the root cause of failure. Based on the results from the Pareto plot, we should focus our efforts on eliminating or reducing the occurrence of the cause that most frequently accounted for failure. In our example, we would focus on eliminating or reducing contamination in the process. That concludes our presentation. Thank you for listening. Alexis demonstrated in SAS while I talked. Jessica.